Bismillahirrahmanirrahim. Assalamu alaikum. This is lecture 6 and we continue with our topic on highway drainage. So one of the important structure for highway drainage are the drainage channels and obviously the side slopes. You can define drainage channels as the channels that are provided along the length of the roadway for taking stormwater drainage, or you can say a rainwater from the pavement surface. What are the requirements of drainage channels? Drainage channels should have an adequate capacity for the design runoff, minimize damage to the highway caused by unusual stormwater, minimize risk for motorists so they don't feel getting into that or they don't fall over because of some inadequate structure design. It should be resistance to the high speed water flows where expected, and it prevents sedimentation of the particles carried by water. So the design consideration for highway drainage include, but not limited to, safety, good appearance, control of pollutant, and economy in maintenance. How we can achieve is by doing these things: providing flat side slopes, the drainage channel should be wide enough, and the rounding of the corners. Now let's take an example how the drainage channel looks like in a plan. So this is my roadway structure, these two lines, and then along with this line the roadside channel here. So obviously the slope of this road section will be going here. What I mean, this portion of the highway is being raised with respect to this. So with all the water coming from the rain or the surface should go here. Now, not only that, there is an intercepting channel, and this channel is also running. Now this channel is taking care of what? It's taking care of the water from the surrounding, from the adjacent tank, and here water is collected from the ground, from the surroundings, and they meet at this point. And this can be connected to the drainage, to the roadside channel as well. So remember, this channel should be wide enough not only to take care of the water from this road surface, but also to take care of the water coming from adjacent buildings or land towards the road. So the point where the roadside channels with an intercepted drain, we call this as toe of a slope channel. Now let's look at side slopes. Steep side slopes improve hydraulic efficiency and reduce hydrophilic cost. Flatter side slopes improve stability and traffic safety, reduce maintenance cost. If you provide slopes 1 to 4, a good chance of recovery for errant vehicles in direct driver tension. Front side channel is visible to the driver. Side slope of 1:5 or 1:6, I mean 1 vertical and 5 horizontal, are recommended in the flat areas. Those intercepting channels have a flat cross sections from a dike made with the borrowed material. Hidden drainage channels are also shallow depressed areas within the inlets. Flumes are open channels of pipes used to connect intercepting channels or shoulders curves with roadside channels. Channel lining prevents channels erosion caused by fast stream of water. Nowadays, channel is also lined with a geosynthetic material, so not only it make it waterproof, but it holds the sides of the channels, not allowing it to erode. The typical example of side slope would be a grass. It is where it is possible. Then there is a concrete, stone, etc. The problem sometimes with the grass is the maintenance. If you do not maintenance, this grass will create a problem, and there may be some uh, some animal hiding there, or this. So it's not very good. Now, what we do in side channel of side slope and what we need to do as a safety is the following. We have rounded hinge points that can reduce the chance of an errant vehicles becoming airborne. For side slope, factor can be negotiated by errant. So in order to have this errant vehicle control, a side slope of 1:5 or 1:6 is always recommended. Then there is a force slope, 1:3 with liberal rounding, provide a good chance for recovery. Slopes cheaper than 1:3 can be used only when used justified by local conditions. The use of roadside barriers should be considered. Maintenance consideration, flat and well-rounded side slopes simplify establishment of turf and maintenance. Slope 1:3 enable the use of motorized equipment. Other rules for side slopes. Flat, well-rounded side slopes create a streamlined cross-section. Advantages for the dead sections are naturally pleasant, natural pleasant appearance, improved safety consideration, snow drift prevented, easily maintained. There are retaining walls that should be considered where slopes would be steeper than 1:2. So if you cannot provide a slope of 1:3, 1:4, consider you have a retaining walls. Standard slab for rock cuts 2:1 is good quality rocks, ranges from 6:1. So sometimes you have to cut the slope, but you have to cut the slope in this ratio, 2:1. Now here is the description of the side slope. So we start with the traffic lane, and then there is a shoulder. And the point where the shoulder and the strong drainage water meets, it's called a hinge point. Slope going towards the drain from the roadway, we call this as a force slope, S1:1. Then obviously there is a slope within the channel that we call a pitch slope, and the point where the force slope and the slope of the channel meet, it's called the toe slope. And now this is the side that is coming from the land side, so that we called a back slope. So the difference between a force slope and back slope, force slope is from the traffic, the water from the traffic, take care from the water from the traffic, and the back slope is taking water from the adjacent land area. This weight is variable, it's very important. The more the weight, obviously, the more water it can take, and also now, but at the same time, it may be economical. Sometimes if you don't have much rainfall, this width can be small. But for an area where high rainfall is expected, this can be quite. There are the other examples of the side slopes. So this is for an rural areas where there is no building around, so you have a section like this. Similarly, if you are constructing a road channel within the urban setup, you can see this as the building line, and with side slope there is a depression over here. The channel is like this. And sometimes not only you have a channel, but you also have a pipe to take care of the extra water. This is the example. This is your drainage channel. This is your intercepting channels. This is another example of the roadside channel. It's a truss, as I've told you, it's stuffed, it's a water. Some of the water is absorbed by the trough, and the remaining is gone. It's allowed to pass through this thing. So this is the channel. So it's not related. This is a road. It's a median channel. You can see. This is a two-way road. The roads, this channel will take in water from this side of the road as well as on this side. Then there is a drainage channel known as curved highways. So the minimum slope varies from 1.25% with intense rainfall will cause wide sheet of water on the curved travel. Or possible improvement maybe have parabolic cross sections with increasing cross slopes. Gutter along the curb with the cross slopes larger than the of the traveled way. On a multi-lane highway or multi-lane traveled way, cross slopes broken along traffic lane edges, increasing from minimum value of the innermost lane up to a maximum value on the outermost. This solution is used in uncurved section as well. So this is a typical example of curved section. You can see this is a curved stone and there is a depression in it. On both sides of the road, obviously the parking is permitted. So on this side you may not provide gutter, but on this side you provide a gutter. Another type of drainage is a subsurface drainage. What is a subsurface drainage? We can define within these lines, moisture changes, the subgrade occur due percolation of rainwater and seepage flows, as also due to the phenomenon of a capillary rise. The aim of subsurface drainage is to keep the groundwater table sufficiently below the level of the subgrade, at least 1.2 meter. When the water table is almost at the natural ground surface, the best option is to raise the formation of the roadway on an embankment such that it is 1.2 meter above the ground. I give you a very simple example for that. If you are constructing a roadway along the water channel like river or lakes or ponds, you must raise the road level at least 1.2 meter or 4 feet from the surrounding. That is, the road level should be at least 1.2 meter high. So what could it do? it will control the phenomena of capillary rise, and the water may not rise up to 4 feet to wet the pavement from the bottom. Now, if this is not possible because of the unfavorable topography, the only option is to lower the groundwater by means of subsurface drainage arrangement. It must, however, be remembered that only gravitational water in the soil can be drained, but not held water, which is made up of the moisture film around the root. This is one typical example of subsurface drainage type. Now what you do, one option is to install a drain in the previous layer, pervious layer, by beside the road to intercept the groundwater before it can reach the subgrade as it shown. So there is an impervious layer. The water cannot be passed or can be hold on. As a layman, you must understand this is a layer not normally made of glaze and like material. So what you do, you provide a pervious layer. This may be of gravels. And what you do, you excavate a trench like this. You have a pipe that we call a perforated pipes. It is so designed that the minimum that the opening should not allow a minimum particle size of around say 0.075 mm to pass through it. Otherwise, if the size of perforation is larger, then the silt will also go and this can choke your system. So what happens here? How does it work? It's the water from the pavement comes to this surface and then it goes like this, and all the water coming from the side of the land side, it enters and it is intercepted. So this is one way to intercept a seepage water that is coming from the adjacent buildings. Now, if the problem is complex, then you have to provide these trenches on both sides. And what this depth is dependent upon the groundwater table. So still we have to raise the pavement by 1.2 meter. So once what you do, you have to have at least this depth more than 1.2 meter. What you do, you build trenches here and here. Once your pavement section is complete, and then you fill this trench. First you lay a sand cushion, and then over it a perforated pipe, and then there are gravels, and then there is a impervious clay seal. So remember, and this is your surface drainage. So what happens, how it works? The water from this carriageway will not be allowed to enter here, but this water may be entering from this point, going down, and at the same time water also be going through this stormwater drainage as we have discussed. Now similarly, the water from this side will go on this side, and from the other side of the building the water will enter here. First the water as such, so what happens, that water will not be allowed to enter this area. So this water, once the water is there, some of the water will go there, some water of the water will go there, some may have this right. And gradually, once you have built this groundwater will also be lowered because all the groundwater will now seep through these trenches. And then they will be collected from the pipe. These pipes may be connected with the interceptor drains, and those interceptor drains will be connected to the water course, whatever the drainage infrastructure you have. Sometimes providing longitudinal pipes may not be enough. So what you do along the length of the roadway, what you do, you also connect these pipes to these longitudinals. So what is happening now? The water will be lowered. When the water goes down, it will be intersected by these pipes. These pipes are staggered for economic reasons. So some water will go here, some water will still seep through, it will go here, this will be intercepted by this transverse drain. Again, these are perforated pipes wrapped with geotextile material so that no clogging occurs. And then once you have done this, this will allow your water table not to come onto the surface, beneath the surface of the pavement. This technically also known as a fresh drain. Another way to prevent groundwater table wetting the pavement subgrade or subbase. Now, if your subgrade is clay, the system on either side will not be effective. In case of very low permeability of the subgrade, such case, the subgrade has to be raised with a free draining material or capillary cut off as shown. This is the capillary. May even of bituminous layers or location should be above the level of capillary expected from the clay subgrade. So when we were talking about the trenches in the previous slide, what we were assuming that the surrounding groundwater table, surrounding ground topography was not clay material. But this is not the case here. The clay material around, so you cannot have a French drain as discussed because this will not allow water to come inside the French. So we'll have to do this thing. Mind you, this is a cheaper solution as compared to the French drains we were studying. So sometimes seepage water renders cut slopes unable by reaching the face of the slope. This can be prevented by lowering seepage line or providing a subsurface longitudinal drain installed to a depth below the pervious layer. If the pervious layer is more horizontal, drains comprising perforated metallic pipes or PVC pipes installed at suitable slope may be provided to serve the purpose. This is the ground slope, and here we have provided a drain. This is the road surface. The water is now coming directly to this, and this is the water. Water from this side we want to prevent entering to this. Another type of a drainage system is what we call a cross drainage. So roadways have to be aligned to cross natural drainage channels, streams, and major rivers. Sometimes the alignment will cross man-made channels like those for irrigation. In such cases, the need for constructing cross drainage structure arises to ensure the water flows beneath the road without causing any inconvenience to the highway structure. 5 major types of cross drainage works: culverts, minor bridges, medium-sized bridges, major bridges, and causeways. Typically, it is the width of the water channel. So, if the width of the water channel is less than 6 meters, the structure that is provided, the bridge structure, is known as culverts. Then 60 to 30 meter, it is called a minor bridge, then medium sized bridge, and the major bridge. And the main difference is also the height of this structure from the water course. These are typical sample of the cross drainage work. We have a pipe culvert. So this is a structure and the water is allowed from the pipe. Another way is to have a box culvert. There is an arch culvert. Now this whole section will allow water to pass. And there is a slab bridge in which you will allow water from the side. Depending upon the capacity, we can have these cross drainage. People are often confused between a culvert and a bridge. So any bridge that is less than 6 meters long, as you can say, it is a culvert. The rest is a bridge. A culvert, height of culvert is lesser as compared to the height of the bridge. Technically speaking, the bridges, as the height of the bridges increase, the cost also increases. As we have seen in one of the diagrams, that the popular culverts are masonry arch, slab culvert, pipe culvert, and RCC box culverts. Then there are causeways. The bridges, the difference between bridges, causeways, and culverts, or we'll say even the culverts and the causeway. The bridges allow water to pass under it. Causeways, in some circumstances, allow water to pass over it. So again, we can say the height of the causeway structures are lesser as compared to the culverts. This again, these causeways should not be provided for a very highly important structure. It is only for small roads, small railroad roads in village areas or rural areas. So as I said, causeways allow water to flow over them when the stream goes to see floods. These are provided on relatively unimportant roads with small volume of traffic. Sometimes you have to close the traffic 15 days, but it's our desire to not to close them at more than 3 days. Depending upon the degree of interruption, we can have a high level causeway or low level. The concept is sometimes we raise the top of the causeway to a expected water level rise. Just like we had a rain in Karachi, and one of the causeways near Baloch colony, it got overflowed. But mind you, for me, it is a high level causeway. Most of the time, you don't have to cross the road, but if the floods are exceptional, then this causeway are damaged and they cannot be open to the traffic. And then, as the name suggests, there are low level causeways. They will be designed at least for 50% above than the expected water level. So it depends upon what level, how you raise your structure. High level causeway is submersible rail bridge to overtopped in floods. Its formation is such a way that not to cause interruption to traffic during flood more than 4 days, 3 days at a time, not more than 6 times in a year. They are provided with the abutments and piers, floors and slabs to form the required. The slope of approaches kept was in 1 in 20. When velocity is high, the aprons of concrete hardened up to a certain distance, then the road can be formed of cement concrete or stone block set in the cement block. A sufficient number of openings are provided to allow the normal flood discharge to pass through them with the required clearance. A low-level causeway provides a bridge when water flows low. Under high flare condition, water runs over the runway, and